Let's jump right into this explainer, shall we? Today, we're diving into Chapter 1, the essential concepts of radiologic science. We're going to uncover the invisible physics that power the incredible world of medical imaging and see exactly how this field seamlessly blends some pretty abstract physics with direct, literally life-saving patient care. To guide us, we've got a fantastic little motto from the author of our source material, Stuart Carlyle Bushong. Physics is fun. And honestly, it sets the absolute perfect tone for what we're doing here. We aren't just slogging through dry math today. We are decoding the secret rules of nature that allow us to literally see inside the human body without making a single incision. It's kind of like having a superpower. Okay, here's our roadmap for this explainer. 1. Matter and energy basics. 2. The language of measurement. 3. Special radiologic units. And 4. Principles of radiation protection. Let's kick things off with Section 1, Matter and Energy Basics, the foundation. Now, before we even get into the weeds of how X-rays are actually made, we have to keep our eyes on the ultimate prize, radiographic image quality. This is the exactness, the absolute fidelity of the patient's anatomy represented on the image. We need this pristine clarity so radiologists can make accurate diagnoses. And that means every single law of physics we talk about today is being manipulated by the radiographer to perfect this one thing. So, with that in mind, get this. Here is a truly staggering statistic about how inefficient this process actually is. Only about 0.5%, literally 0.5% of the X-rays emitted by the tube actually interact to form the radiographic image. No way, right? Less than 1% of the X-rays hitting a patient ever reach the image receptor. Because such a minuscule fraction is doing all the heavy lifting, a technologist's precise control of the beam is absolutely crucial. To measure and control this vast, totally invisible world of X-rays, physicists strive for absolute simplicity. They basically rely on just 3 base quantities: mass, length, and time. That's it. Those are the fundamental building blocks. Every single physical measurement we take in radiologic science ultimately traces its roots back to just those 3 simple concepts. So where do these principles collide in the real world? Right inside the classic X-ray tube. The very instant an X-ray tube is activated, all of those fundamental laws of physics are unleashed all at once. A projectile electron from the cathode literally slams into the anode target, converting kinetic energy into electromagnetic energy. It's this spectacular, invisible physics experiment happening in a fraction of a second, every single time an image is taken. Moving right along to Section 2, the language of measurement, structuring the math. Well, to control those intense forces in the tube, we need precise math. Those 3 base quantities we mentioned, the meter, the kilogram, and the second, they combine to form what we call derived quantities. This is how we translate abstract physics into tangible, real-world measurements. If you want volume, you cube the length. If you want velocity, you divide length by time. This structured math is the universal language that lets scientists exactly communicate what's happening. And that brings us to Section 3, Special Radiologic Units, the Radiologic Lexicon. Standard derived units are awesome for things like velocity and volume, sure, but how do we measure the invisible radiation itself? We need a highly specialized radiologic lexicon that translates standard math into unique, customary, and SI units. For instance, if we're measuring exposure in the air, we use the Röntgen, or air kerma. For the absorbed dose that actually hits the tissue, we look at the rad, or the gray. And to estimate radiation risk, we use the rem, or the sievert. Mastering this specific vocabulary is the absolute key to clinical safety. Speaking of radiation hitting tissue, here's a pretty wild side note. We almost always think of radiation purely as a medical or industrial hazard, right? But naturally occurring radiation is everywhere. In fact, internally deposited naturally occurring radionuclides are actually responsible for a continuous native radiation dose that your own lungs receive every single day. So we are constantly and naturally interacting with the physical forces we're talking about right now. Which perfectly tees up Section 4, Principles of Radiation Protection, Wielding the Power Safely. Now we've reached the most vital part of our explainer. How do we keep you, whether you're the patient on the table or the tech behind the lead glass, entirely safe from these powerful forces? The crucial point here is ALARA, as low as reasonably achievable. And ALARA isn't just a polite suggestion, it is the fundamental guiding philosophy in health physics. Every single action taken in medical imaging is designed to minimize exposure. constantly balancing the absolute need for a diagnostic image against keeping that dose as low as we reasonably can. To actually achieve ALARA in the real world, we rigorously apply 3 cardinal principles of radiation protection. First, minimize time. The dose is directly related to the duration of exposure. Double the time, you double the exposure. Simple as that. Second, maximize distance. Thanks to the inverse square law, stepping just a little farther away from the source drastically drops your exposure. And third, use shielding. Whether it's a heavy lead apron or a protective viewing window, placing dense matter between you and the energy source absorbs the radiation before it ever hits you. But maintaining that patient safety requires a really delicate trade-off. You can kind of think of radiographic quality as a constant balancing act between 3 interrelated characteristics: resolution, noise, and speed. It's a lot like trying to balance coins on the edge of a bill. Even though the speed of the receptor isn't visibly obvious on the final radiograph, it heavily influences the other 2. If you tweak any one of these 3, like, say, altering the speed of the receptor, you inherently shift the balance of the whole entire system. And there are very strict rules governing those trade-offs. For example, fast image receptors are fantastic because they lower the radiation dose for the patient. Win-win, right? Well, not exactly. They inherently increase radiographic noise, that grainy visual fluctuation, and they lower your spatial resolution. So, if you need the highest possible resolution to spot a tiny microscopic hairline fracture, you just have to use a slow receptor, which unfortunately means a higher radiation dose. The true art and skill of the technologist is mastering this exact balancing act. So, we've mastered the building blocks, we've looked at the measurements, and we understand the safety rules that govern standard radiography. But it leaves us with a really fascinating question. As we push into the future and the world of radiography becomes entirely 100% digital, how will these classic rules of physics and image quality adapt? Is digital post-processing going to completely change the way we balance noise, speed, and resolution? It's something to think about, and it proves that while the basic physics remains constant, the science of medical imaging is literally always evolving. Thanks so much for joining me for this explainer. Keep questioning, keep learning, and I will catch you on the next one.